Hi, welcome everybody. Welcome on board. And I would like to welcome Tom. Thank you for joining us, Tom, today. Tom is going to give a talk about getting started with Bluefin. And without any further delay, I'll hand it over to Tom.
So welcome everybody. This is my talk, Getting Started with Bluefin. And Bluefin is a library I've been developing for Haskell over the last year or so. So in this workshop, which lasts about 45 minutes, I'm just going to give you the very basics that you need to know to get started with Bluefin. And if you'd like to follow along with the coding that we're going to do, then you can have a look, excuse me, you can have a look at this GitHub repo, which you can clone and you can run using your own Haskell tools. But you don't have to if you just want to just watch what's going on. That's also fine. The link should also be posted in the chat here, and the link is also on the talk page of this talk in the Functional Conf website, so you can find it in both of those places. So again, whilst this slide stays up, you've got the link here if you want to go and clone that. So a quick introduction to Bluefin and an introduction to me. So my name's Tom Ellis and I work at a firm called Grok. At Grok, we're developing the world's fastest AI compute hardware for AI inference of things like large language models. And we are using Haskell, at least in some part of our tool chain, particularly our compiler tool chain, also for our CI systems, and also we use it a bit in hardware design also. So we're happy users of Haskell at Grok, and we're happy users of Bluefin also. What is Bluefin? Well, Bluefin is what's called an effect system in Haskell. And that is a library or a package which gives controlled access to a variety of different effects that happen during the execution of your program. So there are some examples. For example, state effects. This is the way we refer to mutable values in our program that you can modify, update, read and write as the program progresses. There are also exceptions. So those are exceptions that you might be familiar with from more imperative languages, but also Haskell itself has exceptions in its IO monad. But Bluefin gives you access to exceptions in a more controlled way. We'll see a bit about that in a moment. Bluefin also gives you access to streams. Those are, for example, like streams you might be familiar with from Python, also called generators or iterators. You get the ability to yield values from a function as you're processing the function and then collect those values at a different part of your code. And of course, we want access to IO. So in Haskell, the IO monad is the way that we interact with the external environment, amongst many other things, to read and write files, to access the network, and all sorts of features. In fact, pretty much every feature in Haskell that involves interacting with something outside your program is done through the IO monad, and Bluefin also gives you access to the IO monad itself. And there are many more things you can do in Bluefin besides that, many more effects. So hidden in this, etc., is quite a long range of different features, different facilities you can get access to. But today we'll just focus on these four because these four are really the basic building blocks of Bluefin and what everything else is built on top of. So we will just be looking at some Bluefin basics today, but the aim at the end of the workshop is that you have enough familiarity and comfort with it to download the example package from GitHub, play around with that and extend it with some of your own examples, and to maybe start playing around with Bluefin and some code that you're writing yourself. So this workshop does use do notation and monads. If you're familiar with those, then you should be able to follow the code straightforwardly. If you're less familiar with Haskell and those particular concepts in Haskell, then that's fine. You can also follow along just by watching, and it might be a nice introduction to those concepts for you, but it will mean that you'd be less able to jump in straight away and get your hands dirty with Bluefin. But that's fine. Hopefully that will serve as a launching point for you for your journeys with Haskell and with Bluefin. So let's look at a very simple example that uses a state effect in Bluefin. This function is called total price, and what it's doing is it's taking a list of prices, which are integers, and it's summing all of those prices to get a total price. So this is basically a sum function written in Bluefin. Let's start from the top. Well, many of the examples we see are going to be wrapped in this run pure f function. This is a Bluefin function which basically says, do all the effects that are that appear in the code beneath me. So actually what's doing the job is all of this underneath. So we're going to primarily be focusing on this. So what is this doing? The first thing it's doing is running eval state, which is saying, introduce to me a new mutable state. And I want its value to be initialized to 0. And I want it to be called total. So total is a mutable state. We can pass this thing around and perform various operations on it. It contains an integer which starts with value 0, and we can change that value as our program progresses. So in order to add up all of the integers in the input list, which is called prices, we iterate over all of the prices with what effectively is a for loop in Haskell, but in Haskell it's not a built-in construction, a for loop. It's just a function called for, and in fact it has an underbar in the end, on the end, the particular one we want in this case. So this says iterate over all of the prices, one at a time. So for each price, we get the price value here in this variable called price. And what we're going to do is we're going to modify our total by adding the price to it. So we start at 0. Every new price we see, we add it to the total. And at the end, the total contains the sum of all the prices coming in. And the final thing we do in this effectful operation is we get the total. So we get the final value of the total. And what happens if we run it? Well, here's total price adding up 5 numbers from 1 to 5, and we get, as we expect, 15 as the result. Let's now have a look at how we use exceptions in Bluefin, unless there are any particular questions about this state example, which I can answer now.
Nothing right now, Tom.
So let's proceed to an exception example. So in fact, what I'm going to show you here is a particular use case of exceptions called early return. So you might be familiar with using exceptions for raising error conditions, flagging error conditions during program runtime. But another use of exceptions is just being able to exit early from a particular function or from a particular block of code. So that's what we're going to do here. This contains item function is going to take the name of a particular item. So in this case, we're looking at items of clothing. And we're going to see if it exists within this basket of items of clothing. So we're going to search for what's called sort item within the basket. And if sort item exists in the basket, we're going to return true. And if it doesn't exist in the basket, then we're going to return false. So again, the top level is this run pure f thing, but where the job is done is everything beneath the run pure f. So it's this block of code here. And how we start is using this with early return. With early return introduces into our program this thing called ret here, and I call ret an early return handle. It gives us the ability to return early to the block created by with early return, rather than just stepping through till the end of the code of with early return. So normal evaluation of this block just proceeds top to bottom, statement by statement until the end. But by using this handle ret, I can break out early from the block. So let's see how we use it in this case to find out whether the item exists within the basket. Well, we have a for loop again. So we're iterating over all the items in the basket with this for basket. And we get each item bound to this basket item variable. So if the basket item variable we're currently looking at is equal to the one that we were looking for, well, that's great. That's exactly what we wanted. So we can return early and say true. We found it. Great. When that happens, control flow returns to where the with early return was written, and then we just continue. If there was more code down here, then we just proceed with the code down here, and everything else in the with early return block is skipped. So this is very much how exceptions work. IO exceptions in Haskell, but also exceptions from any other language you might be familiar with, except here we're using them explicitly to return early and jump out of a block. So let's have a look at what happens in a particular example. Well, if we're looking for hat amongst this basket, well, it does exist. That's great. So we get true, as we expect. If we're looking for hat in this basket, well, it doesn't exist at all. So we get false, as we expect. Any questions or thoughts or comments about that from anyone? Because next we're going to proceed to looking at some streams, but I'll handle any questions about exceptions.
Nothing else now, Tom.
Okay. So here is an example of using streams in Bluefin. The function is called product combinations, and what it's going to do is it's going to take a list of possible colors. So that's a list of strings called colors. It's going to take the name of an item. So that could be hat, shorts. And it's going to take a list of possible sizes. That's in this sizes variable. And it's going to produce all possible combinations of colors and sizes for that item. So again, we have run puref at the top level, and everything that's happening is being done below that run puref in here. So we're going to look there. The first thing that we're going to do is we're going to run yield to list. And what yield to list does is it gives us a handle to a stream that's called y, and we can yield elements to y in order to put them on the stream. And yield to list will pick them up off the stream and it'll put them into its result. And its result here is called combinations. So in order to find all possible product combinations, we are going to iterate over the colors with a for loop. And each color we see is going to be called color in this variable. We're going to iterate over all the sizes, and each size we see is going to be called size in this variable. And then for that particular combination of color and size, we're going to yield to the stream just that combination. So we're going to yield the color, the item, and the size separated by spaces. And we're going to collect them all together, or yield to list is going to collect them all together into combinations. So let's see what that looks like when we run it. Well, here I am putting in blue, green, and yellow as the colors, and small, medium, and large as the sizes. And I get one item for each possible combination. That's 9 in total in this case. So I've got a blue shirt small, blue shirt medium, so on and so forth, up to yellow shirt large. So these streams work in a way that is quite similar to Python's iterators or generators, if you're familiar with them. And in the Haskell world, there are streaming libraries such as pipes, conduits, and there's one called streaming itself. And these streams work in a similar way. But you'll notice in these three examples that we've seen so far, streaming, exceptions, and state, you always get this thing, which I call a handle, which gives you direct access to the capability in question, to the effect in question. In other Haskell libraries, pipes, conduit, and streaming, this handle is kind of implicit. You don't get a handle that you can directly yield stuff to. You just yield, and the place to yield to is sort of implicit. It's just taken out of the air. So recall that in the with early return example, we had this handle to return early. You can explicitly mention this ret, or if in fact you have to explicitly mention this ret when you say where you're returning to. In imperative languages where you have early returns and you have break statements and continue statements, the place that you return or break or continue to is always implicit. And in Bluefin, it's explicit, so you can see exactly what's happening. You could have two nested early returns here. You could choose which one to return to based on an explicit usage of the handle. And the same for state. You have an explicit handle to the state, but that's kind of more familiar. In any language with mutable variables, we're used to having a variable that we mention by name. So that's a more familiar case. So I'll take any questions now about streams or anything that's happened up till now. And if nothing, or after that, then I'll proceed to just editing a few files. Well, these functions that I've shown you, making some small changes and seeing how we can change to get different behavior.
I think we can proceed, Tom. No question as of now.
Let's do that. So this is the code from the Git repository. And this is the total price function, which we saw before. So it starts with state 0, and for every price, it adds that price into the state. So I can do total price of 1, 2, 3, 4, 5, and get 15. If I wanted to multiply them instead of add them, well, that doesn't make much sense for a price as such, but let's see what would happen. Then I could multiply them. In fact, we'll see when I reload and run this, that doesn't give me the multiplication of 1, 2, 3, 4, 5. It gives me 0 instead. Well, what's gone wrong? It's because I didn't change the initial state. So I need to make sure that I change the initial state also. This has started with 0, and it's multiplied many different numbers by 0. But when you multiply any number by 0, you just get 0 out. So that was a mistake. We have to go back in and fix that. I want to start with state 1. So now if I do the same, I'll get 120. That is the product of all these numbers from 1 to 5. Let's see what happens with contains item, which was our usage of early return. So this is an example we had to see whether this list contains hat. Well, it does, and it says true, as we expect. Great. We could change this a bit. What can we make it do? We could change it to determine whether every item in here is the sort item. So actually, I will copy this and call it every item. So I only want this to return true now. If I put in hat for sort item, if every item in the basket is a hat. So how do I need to change that? Well, If the basket item is not the sort item, then I return false. And if I went through this loop and I didn't return false, then every item must have been the sort item. So then I return true. So is every item a hat in the list of hat, hat, hat? It says true. But hat, hat, shirt, this should be false. There we go, as expected. Great. And for product combinations, well, this is the example we saw of different shirts with different colors. I'll run that one. So 9 results as we had. If I want to be able to vary the items as well, how do I do that? Well, I want to be able to put in a list of items, so not just one item anymore. And then for each item, I want to yield every combination with that particular item. So let's slightly change what we are feeding in here. Let's say product combinations. Oh, well, I can get the same behavior as before by just saying, well, I only want a list. So I'm putting a shirt in a list of just one element. So here we have 9 again. This is exactly the same output because I've just said, well, I only want items which are shirts. But if I want to have other items, so I'm going to have small and large, blue and green, let's say shirt, and what should I have? Shorts. So here I get 8 possible combinations. Blue shirt small, all the way up to green shorts large. And there's one more change I want to make here, which is I just want to say, well, let's say green shorts large. Let's say green shorts at all are not allowed. So I want to say when the color and the item is not equal to green shorts, only then am I going to yield this result. So this is only going to yield items that are not green shorts. Let's have a look at that. Here we go. So we had green shorts in the output before, but now it's gone. We had these green shorts large in the output before, and now it's gone. So by just having some normal Haskell logic here and guarding the yield to the stream by that conditional, we can change the kind of things that we output. So any questions or thoughts on that? And if not, I will move back to some more slides.
I think let's continue.
So now I want to show you what effectful operations look like under the hood. And by under the hood, I mean without that run pure F. Previously, we saw the result of just running operations. So if I skip back to the previous slide, this run pure F was running all of the effects within its block. Well, what if we don't do that? What does it look like? Well, it means we have to pass in as an argument to our function the stream. So this is the same function as before, except we're just not running the effects yet. So I have to pass in the stream that I'm going to be yielding the values to. And when I do that, well, I pass in a thing of type stream string, which makes sense because it's a stream of strings. But also there's this E1 type parameter on the end. What does that mean? Well, if we look up at the constraints, we see here, I read this as E1 is in ease, and ease is the name, is the type that the resulting effectful operation is parameterized by. So this E1 in ease means that this stream can be used within the effectful operation. If we didn't have this at the top, then we wouldn't actually be able to at all use this stream string E1 within this function. So all Bluefin operations that take handles as arguments, so handles such as streams, exceptions, states, and so on, they always have this form. You have a type variable on the handle. The type variable must be in the overall effect type of the effectful operation that you see here. And otherwise, this block is exactly the same as we just saw in the stream example. So what happens if we have more than one handle go in? Well, I'm going to show you an example now that has more than one handle go into a function as an argument. And also, we're going to see our first usage of IO in Bluefin. So we're passing in two handles. One is called IOE. This is a handle that allows us to do IO effects. We're passing in another handle, which is the early return handle, which does the early return job we saw previously. And this is a similar, it's a combination of things that we've seen previously. So what's happening is that I'm using for each to loop over a stream, an operation that has stream effects. So this product combinations is from the previous slide. And what it does is it produces all combinations, all possible combinations of items. So green hat small and blue shorts large, for example. And for each is looping over each one of those, and each one of those will be called item when we get it. And we're checking whether the item that we get was the one that we were looking for. If so, we say, yes, we found it. And then we return early, saying true. So when we find the item we want, we're actually doing two things now, whereas previously we did one. Previously we returned early and said, yes, we found it. But here also we're printing something to the screen using the IO handle. The IO handle is called IO. That's this argument here. And we're using it to print something to the screen. And the way we use it is we run this FIO function. We pass it in, and then we give a Haskell IO action to perform. Now, what happens if we come off the end of this loop? If we come off the end of this loop, then we didn't find our item. So that means that the item wasn't in the list. And here we do two things also. We say that we didn't find the item by printing it to the screen, and we return early and say false. We didn't find the item. And in fact, here we could, here we have to return early, whereas in previous examples, we could just put pure false and fall off the end. In this particular case, we're designing the function so that we always return early. And in fact, this A here, which is the return type, essentially means that it's impossible for us to have normal return from this function. We always have to return early through this early return handle. Okay, so we now understand what this does, but we can't actually use it because we don't have these handles lying around to pass in. How do we get them? That's what we'll see next. When you're running some combined effects, so the function from the previous slide is here, find my item. You bring the handles into scope with the handler functions. We've already seen with early return in some previous examples. That brings into scope an early return effect. And because it's just a because it's just a Haskell value, we can just pass it in as the argument to find my item f. So if I go back and show you the type of that function, find my item f, well, the second argument of find my item f is this early return thing. So we can just pass that in as an argument. It expects the capability or the handle to be able to return early with a bool, with true or false. So that's what we're passing in here. The other thing we need to do is we need to get access to I/O. And previously in the examples, if I skip back to an earlier example, we saw that the effectful functions we were running were being run with run pure f. Run pure f is for ones that don't have any access to I/O. But because we are doing I/O here, we use the one instead that is called runf. And when we use the runf handler, it gives us access to a handle of type IOE. Let's go back to the type of find my item f. We needed an IOE to be passed in as the first argument to find my item f. So this is what we're doing here, getting access to a value of type IOE, and then we're passing it in as this item, this argument here, and then we have all the arguments that we need in order to run find my item f. And because we're at the top level, we're running the runf, it means that the entire body of code will then execute to give us a result in I/O. And it will be a Boolean, true or false, saying whether we found the item or not within the list of items. So let's have a little, let's see a little example of how this runs in practice. Here's the first one. Find my item. I am I'm going to search for a yellow shirt medium. So this is actually the this is the second argument of the function. That's this argument, but it's fallen off the end of the line because the line's too long, so that's wrapped around. So that might look a little confusing, but this yellow shirt M here is the second argument to find my item. That's the sort item. That's what I want to find. And I want to find it in all of the combinations of colors blue, green, and yellow of the item shirt, and for all sizes, small, medium, and large. So what happens is it says, yes, I found the item, yellow shirt medium, and it returns true. So if we go back to find my item f, which is how this function was implemented, we can just refresh our memory. When it found the item, so when the item was that we were looking at as we were iterating, was actually the one that we were seeking, then what it does is it prints out that it found the item, and then it returns early saying true. So that's what's happened here. It's printed out that it's found the item, and it's returned early saying true. What happens if the item does not appear amongst the combinations? Well, here we're looking for something called gray shirt extra, extra large. Now this won't appear amongst the combinations because, well, there isn't a gray color at all, and there isn't an extra, extra large size. So we will iterate through all possible combinations of these colors and sizes, getting blue shirt small and so on and so forth up to yellow shirt large, but it will never see a gray shirt extra, extra large. So what it's going to tell us now is, didn't find an item, and it's going to return the value false. Let's go back to the previous slide again, just to have a look at why we got that result. Well, this for each loop was iterating over every combination, and during its execution, if we found the item we were looking for, then we returned early with true. That's what happened in the last example. But in this example, with gray shirt extra, extra large, this condition was never satisfied. So we never ran this block of code. We never returned early, and we just fell off the bottom of the for each loop. We just exited from that for each loop just completely normally. So when that happened, we then proceeded to execute the next lines of code. And the first one is using the IO capability, using FIO to use the IO capability to run an IO action, and it's going to print to the screen, didn't find the item, and it's going to tell you which item you were looking for. So if we go back to the output, it didn't find the item gray shirt extra, extra large. That was the one we were looking for. It wasn't in any of the combinations. And then it returns early with the value false. And that's exactly what's happened here. The overall result of running this Bluefin action as a Haskell IO action of type IO bool, well, the bool that's being returned is false. So that is how we got to this stage of execution. So now let's have a quick look at the code for these examples and play around a bit. What can we do?
Tom, now,
Yes,
okay.
sure.
I'll just read it for you. So Ned is asking that he's not familiar with Haskell, but it looks like Bluefin provides the ability to incorporate effects in the middle of the code flow. So his
Yeah,
question
that's right.
is, are there any other advantages to using Bluefin?
So Bluefin is the latest in a long line of effect systems in Haskell, and I can give a short overview of how we got here. So early on in the development of Haskell, well, it was developed to be what's called a pure functional programming language. So pure means without effects in a sense. And this was a sort of philosophical conundrum because we want our programs to have effects. We want to be able to print things to the terminal, read files, open network connections, to be a useful language. And then early on, a few years after Haskell was introduced, they settled on this notion of monadic effects. So there was a sort of, well, it's called a type class in Haskell. It basically means an interface. There's a way of specifying how certain data types in your language can be seen as sequences of statements, one after the other, to be executed by the program. And that's great because it allows you to do all sorts of effects, whilst you can do what's called IO. That's a monad. It's an instance of the IO of the monad type class. So it's an instance of this interface called monad, and it allows you to specify IO actions to be performed one after the other. So this is interesting because, in a sense, you could then say Haskell isn't a pure language. It allows us to access the outside world. So it's not just sitting there on its own doing its own numerical calculations. It's actually interacting with the world. So the way I see this is that not that Haskell is pure per se, and I don't think that's a very useful way of looking at it because that's more of a sort of philosophical problem than a practical explanation. So I like to think of it as giving access to fine-grained effects. So if I look at some of the examples here, the benefit of doing effects this way is that this find my f function can only do IO actions and do early return. It cannot modify any mutable state. It cannot write anything to any streams because those parameters are not being passed into the function. So that's the nice property of using these sort of fine-grained ways of modeling effects in Haskell. You can be a lot more sure about what your program can do and what it can't do, which is very nice for dealing with large software systems.
Thanks.
Now, in the intervening period, there were many different attempts at different libraries called effect systems for providing effects in a variety of different ways that are composable. You can build up bigger programs out of smaller ones and give you access to all the effects that you need. One of the early ones was called monad transformers. More recently, we've had Fourier effects, we've had polysemi, and over the last few years, one effect system called Effectful has become very popular, and Bluefin is really a descendant of Effectful. The only difference really between them is that Effectful doesn't have these explicit handles. Instead, it puts them into type class constraints. So instead of IOE appearing here as an argument, it would appear here as a constraint. And I prefer having the explicit arguments.
Tom,
And
sorry to
some people
interrupt.
prefer constraints. Yes.
We have 3 minutes to go, just letting you know.
Okay, in that case, I will. I'll just finish this story, and if we want to have a look at some more code, we can then take that to the Hangout rooms afterwards. So yes, to finish the story quickly, I think the effectful way of doing things is I think it's the best approach for Haskell. That's why Bluefin is following the effectful way. And underneath the hood, effectful and Bluefin are actually using Haskell's IO directly. So they're actually using this IO type directly. And what they do is they carve IO up into smaller ranges of effects so that you can't do every possible IO thing in your program. So for example, if I see something of type IO bool in Haskell, I don't really have a very good idea what it does. I know that it eventually returns a Boolean, true or false, but in this IO, it could do all sorts of things. It could be opening network connections. It could be writing files to disk or reading them. It could be printing anything to the terminal, all sorts of things. Whereas the one written in terms of Bluefin, I know that it only does this early return. Well, maybe this isn't a very good example because this IOE allows it to do many things. But if we didn't have the IOE here and we decided I'm not going to print out anything to the terminal, then I would know that the only thing that this function can do is return early. It's the only effect that it can have. Can't do anything more than that. So that's very nice for architecting large-scale software systems. So I'll wrap up this talk now. And then if people have other questions, they can come to their Hangout rooms and ask there. And I can show more code examples if people want to see that.
Yes, thank you so much, Tom. Thank you for such a
Pleasure.
wonderful
Thank you.
Ned is also thanking you. He's saying sorry for taking so much time, but
That's
the
okay,
code
Ned.
is.
It's a good opportunity to explain. Yeah.
So with that, I'll just end this session. Once again, thanks, Tom, and thanks, everybody.